In this video, I'm going to be talking about how to solve a roller coaster problem using energy. The main concept behind solving roller coaster type values is taking a look at the total mechanical energy. The total mechanical energy is the sum of the kinetic energy and the gravitational potential energy. So basically taking a look at its energy of motion and how fast it's going, combined with its energy stored through its height and its location and how high the roller coaster is rising and falling. So if you take a look at a roller coaster over here, the very first hill is the highest peak and the greatest height of the roller coaster. And just like anything else, it has to have work done on it in order to gain energy. So a chain lift will pull the roller coaster cart up to the top of the hill. It will do work transferring energy to the cart and the people so that it has its total mechanical energy to go through the ride. Now, at the very beginning of the ride, it momentarily has a velocity of 0 meters per second before its drop. So it won't have any kinetic energy at the top of its very first hill, but it will have lots of gravitational potential energy. So in order to solve for the total mechanical energy, you would set it up just like this. Alright, I've went ahead and solved for the total mechanical energy of 78,400 joules. So we know it's the sum of the kinetic and the potential energy, and for our first hill, it's pretty safe to assume that it has an instantaneous velocity of 0 meters per second. Therefore, if I plug in that 0 into my kinetic energy formula, I end up with a kinetic energy of 0 joules. So all we have to do is plug in our three values for our gravitational potential energy to find our total mechanical energy. Our mass of the cart and people is 400 kilograms, times a G value of 9.8 times a height of 20 meters. Once you find the product of those three, you find a total mechanical energy of 78,400 joules. Now that's going to be the key number to solving for a lot of our values throughout this problem. So if you take a look at position B, C, and D, we have some information about those different locations in the ride. For each of those, we will have to use this value. It's going to be a key value in solving for what we need. So what I'm going to do is I'm going to use that total mechanical energy, some of my values in the box over here, and then I'm going to solve for values for potential energy, kinetic energy, and then solve for some velocities and heights as well. Now that I've finished solving for all the values for position B, C, and D, we're going to go ahead and take a look at the details of how we got these values. So as I said before, the main concept is the total mechanical energy equaling the sum of the kinetic energy plus the gravitational potential energy. We had enough of the information from this box over here to fill out what we needed for the potential energy formula. We had the mass of 400, we had a G value of 9.8, and we had the height of 8 meters for position B. So if you go ahead and take the product of those three, we can find the potential energy. And then our only unknown is kinetic energy. So after you subtract the 31,360 joules from each side, you find the remaining energy, which is 47,040 joules for the kinetic energy. Now, when you want to find something a little bit more specific, like the velocity, all you do is take that, plug it into your kinetic energy formula, and then set it equal to 1/2 mass times velocity squared, which is exactly what I did. If you take the 1/2 times 400, that gives you 200. So I simplified it down to 200 times v squared. And then you have to do two more steps to solve for the velocity, which is divide both sides by 200 and then square root the v squared so that you get your value for v. And we get 15.3 meters per second, which is a pretty high velocity because you have very little gravitational potential energy at this point here because it's dropped so much. A lot of it's converted into kinetic, therefore having a very high velocity. At position C, all the steps are very similar. The only thing that I changed is this 17 meters from the height. So as it rises up to a much greater height, it has a lot more gravitational potential energy and much less kinetic. As you can see here, it goes from 47,040 joules to 11,760 joules. So you're going to go ahead and plug that into the KE formula, do all the same steps as we did in this box over here, and you end up with a velocity of 7.67 meters per second. For position D, our speed was given for that position. It was 19 meters per second. So instead of plugging in mgh to solve for the potential energy, I went ahead and took 1/2 times m times that v of 19, squared it, and I came up with 72,200 joules, which I subtracted from both sides in order to get the gravitational potential energy of 6,200 joules. Now, just like we saw for the velocity, we went ahead and took that 6,200 joules and set it equal to the mgh. We had the m of 400 kilograms, the g value of 9.8. If you went ahead and multiplied those two, you get 3,920 times that h still. So it's just one mathematical step after that, which is dividing both sides by 3,920, which leaves you with the final height of 1.58 meters. So to recap on the main ideas of what we did, typically you analyze the first hill and you have to find the total mechanical energy by plugging in a velocity of 0, which leaves you with a kinetic energy of 0, and then plugging in all your values for the gravitational potential energy to get your total mechanical energy. From there, you have to get other values to work with, which are typically heights and velocities, and then from there you proceed using the steps that we talked about in each of these different boxes. I hope that was helpful in helping you solve a roller coaster problem using energy. Thank you for watching and listening.